At 1:34 in the morning on April 23, 2026, while the big island of Hawaii lay in full darkness and nearly everyone on it was asleep, a column of molten rock punched out of the earth and began climbing into the sky. It did not stop at 10 stories, it did not stop at 20, it did not stop at 50. By 3 in the morning, peak north vent lava fountain heights of approximately 1,000 feet, 300 meters, were reached, along with peak eruptive plume heights of about 20,000 feet above sea level. USGS 1,000 feet of molten rock, rising from a vent in the floor of Halemaʻumaʻu crater, climbing to the height of a 100-story skyscraper. Not a building, not a structure of steel and glass designed by engineers over years. Liquid rock, fired into the Hawaiian sky in the middle of the night, by a force that has been operating on this planet for 4.5 billion years. Doing it again, doing it for the 45th time since December 2024, doing it exactly when the scientists predicted it would. And still doing it in a way that no human being can fully predict, fully explain, or fully stop watching. This was episode 45 of the ongoing eruption of Kīlauea, and I want to spend this entire video on one question. How? How does the Earth do this? How does a mountain produce a 1,000-foot column of liquid rock in the middle of the night, and then, 8.5 hours later, stop completely, as if someone turned off a switch? How does the volcano know, and I use that word loosely, to pause for 14 days, recharge, and go again? What is happening underground during those pauses that makes the next eruption inevitable? What is a gas piston? And why does the strange rhythmic behavior inside the vent during the quiet periods between episodes matter so much to understanding why episode 45 looked the way it did? And what does the fact that this is the 45th time in 16 months tell us about where this eruption is heading? Let me begin at the bottom, not at the crater floor, not at the magma chamber a few kilometers beneath the summit. I mean the actual bottom. The place where this story starts, which is roughly 60 kilometers below your feet if you are standing on the big island. That is where Kīlauea's magma originates, fed by one of the most powerful and most ancient geological structures on Earth. The Hawaiian hotspot is generated by an upwelling zone of hot rock called a mantle plume that intermittently pierces Earth's crust. As the mobile Pacific plate carries active volcanoes away from the underlying plume's largely stationary source of molten rock, the volcanic features fall dormant. Meanwhile, the moving tectonic plate brings a previously unaffected area of crust over the plume, and a fresh zone of volcanic activity springs forth to build new islands. USGS volcanoes. This is why the Hawaiian island chain looks the way it does, a string of islands and drowned seamounts stretching 6,000 kilometers northwest across the Pacific, each one older than the last, each one a former Kīlauea that has been carried away from the heat source and gone cold. The big island is where the hotspot sits right now. Kīlauea is the currently active expression of a mantle plume that may extend all the way to the core mantle boundary, 2,900 kilometers below the surface. Geophysicists believe that hotspots originate at one of two major boundaries deep in the Earth, either a shallow interface between convecting and non-convecting layers in the lower mantle, or a deeper layer approximately 200 kilometers thick immediately above the core mantle boundary. The Hawaiian hotspot temperature is estimated at about 1,500 degrees Celsius, compared to approximately 1,125 degrees Celsius for mid-ocean ridge basalt. USGS. The 175-degree difference matters enormously. It means the Hawaiian hotspot is producing magma that is hotter, less viscous, and more capable of traveling rapidly to the surface than most other magma on Earth. By the time that magma reaches the eruption vent at Kīlauea's summit, the eruption temperature of Kīlauea lava is about 1,170 degrees Celsius, 2,140 degrees Fahrenheit. USGS. That is hot enough to melt steel. It is roughly 6 times hotter than the highest temperature a home oven can reach. It is hotter than the surface of some dim stars. And at that temperature, basaltic lava flows and moves with a fluidity that is fundamental to everything that makes a Hawaiian eruption look the way it does. This is the point where Kīlauea starts to diverge from the image most people carry in their heads when they hear the word volcano. Most people think of a stratovolcano, the steep, conical shape of Mount St. Helens or Mount Fuji or Vesuvius. Those volcanoes are built from magma that is high in silica, which makes it thick, sticky, and resistant to flow. When gas tries to escape from high silica magma, it cannot move through the viscous melt quickly enough. Pressure builds the magma fragments. The eruption is explosive in the most devastating sense. Not a fountain, but a lateral blast, a pyroclastic flow, a column of ash that can reach the stratosphere and circle the globe. Kīlauea does not work that way. Hawaiian eruptions are typically effusive, with basaltic magmas of low viscosity, low content of gases, and high temperature at the vent. Very small amounts of volcanic ash are produced. USGS low silica, high temperature, thin and runny. The lava at Kīlauea is, as volcanologists sometimes describe it, closer in behavior to very hot motor oil than to the thick, slow paste of a high silica magma. And that difference in viscosity is the entire reason why episode 45 produced a 1,000-foot fountain of liquid fire, rather than an ash cloud that could circle the planet. Now let us talk about the gas, because the gas is the engine. Everything about a lava fountain, its height, its intensity, its duration, the specific shape it takes, comes down to what dissolved gases are doing inside the magma as it rises. In a double handful of molten magma, weighing about a pound, there is less than 1/10 of an ounce by weight of dissolved gas, roughly the same weight as a pinch of table salt. Yet this tiny amount of gas can drive spectacular lava fountains hundreds of feet into the air. The fountaining occurs because dissolved volcanic gases expand when pressure on the magma is released. Anyone who has shaken a bottle of soda and opened it quickly has gotten the full value of this basic principle of physics, USGS. The pressure inside a sealed soda bottle keeps the carbon dioxide dissolved in the liquid. The moment you remove the cap and reduce the pressure above the liquid, the gas comes out of solution and expands into bubbles violently and immediately. Kīlauea is doing the same thing, at a scale and a temperature that the analogy cannot fully capture, but the physics is identical. The dissolved gases in the magma, primarily water vapor, carbon dioxide, and sulfur dioxide, are held in solution by the immense pressure of kilometers of rock above them. As the magma rises and that pressure drops, those gases exsolve. They come out of solution. They form bubbles. The bubbles grow. The bubbles want to expand powerfully because the gas that was compressed under hundreds of meters of rock suddenly has room to become what gas wants to be, vapor, expanding freely in every direction. At Kīlauea, carbon dioxide begins to bubble out at very great depths, 50 to 60 kilometers beneath the surface, while sulfur dioxide will only bubble out substantially once the magma reaches a few hundred meters to a kilometer below the surface. Big Island video news. So the gas payload that drives a lava fountain has been building since the magma left the mantle source dozens of kilometers below the ground. The carbon dioxide starts exsolving at the very bottom of the journey. The sulfur dioxide joins in at the last kilometer or so. By the time the magma is approaching the surface, it is not just molten rock anymore. It is molten rock foaming with expanding gas, a two-phase mixture of liquid and vapor moving upward at speed, and when that mixture reaches the narrow opening of the vent, the gas expansion launches the liquid into the air. The fountain gains its momentum by the expansion of gas bubbles that dissolve from the magma as pressure falls while it is rising in the conduit. Strong fountains can reach several hundreds of meters. Hawaii, Tribune Herald. For this to produce a fountain rather than an explosion, the key is that the gas and the liquid have to stay coupled together all the way up the conduit. In high viscosity magmas, the gas separates from the melt before it reaches the surface. It moves faster than the thick magma can follow. It arrives at the vent alone or ahead of the lava, and the remaining melt fragments explosively because the gas that was supposed to carry it up is already gone. In low viscosity Hawaiian basalt, the gas and the liquid travel together. They rise as one. For low viscosity magmas, bubbles coalesce and recover a spherical shape within 3 seconds, implying that for lava fountaining activity, gas and melt remain coupled during ascent up to the last 100 meters of the conduit. USGS volcanoes. The last 100 meters. That means that for almost the entire length of Kīlauea's magma conduit, through kilometers of rock, the gas and the lava are moving as a unit. Only in the final 100 meters, as the pressure drops most sharply and the bubbles grow most rapidly, does the mixture begin to separate into the jet of gas-driven liquid that becomes the fountain. The vent opening is the nozzle. The expanding gas is the propellant. The lava is the projectile. And the result, at its peak during episode 45, was a column of incandescent liquid rock rising 300 meters into the Hawaiian sky at 3 in the morning, illuminating the crater walls and the plume of volcanic gas climbing to 20,000 feet above sea level, while the island slept. Lava fountaining intensified rapidly after onset. Fountain heights increased from 150 meters at 2:18 in the morning to 300 meters by 2:45 in just 27 minutes. Scott's Coop. That escalation rate is telling you something specific about the plumbing system. The fountain got taller in 27 minutes because fresh, deeply sourced, volatile-rich magma was arriving at the vent faster than the episode had initially released it. The gas content of the magma feeding the fountain in those early minutes was climbing as deeper, less degassed magma caught up to the eruption rate at the surface. The heights of lava fountains and Hawaiian-style eruptions are controlled by magma gas content, volume flux, and the amounts of lava re-entrainment and gas bubble coalescence. Hawaii volcano expeditions. What this research tells us is that fountain height is not a simple single variable measurement. The volume of lava moving through the vent per second matters. The degree to which already erupted lava droplets falling back toward the base of the fountain get pulled into the jet and relaunched matters. The size to which gas bubbles have coalesced before they reach the surface matters. Episode 45's peak at 1,000 feet was the product of all of these variables aligning during those first hours of the episode, when the magma supply was at its freshest and most volatile rich. By 7 in the morning, steady fountaining from the north vent continued to reach near 700 feet, producing what Hawaii Volcanoes National Park described as a beautiful pa'u, or skirt, of lava spreading onto the Halemaʻumaʻu crater floor. Big Island Video News, the pa'u, the skirt of lava. That image is exactly right for what a Hawaiian lava fountain looks like at the base during sustained activity. The central jet rises to whatever height the gas content drives it. The droplets of lava thrown outward at the top of the jet fall back down, some cooling midair into glass fibers and glass teardrops, Pelly's hair and Pelly's tears, others still liquid enough to land as spatter and spread outward in every direction, forming that skirt around the base of the fountain, adding new material to the growing lava field on the crater floor. Every episode adds to it. 45 episodes since December 2024. The topography of the crater floor has been fundamentally changed by this eruption. And then, at 10:01 in the morning, episode 45 ended abruptly after 8. 5 hours of continuous lava fountaining, the USGS lowered the volcano alert level from watch to advisory, and the aviation color code from orange to yellow. USGS volcanoes abruptly. That word is used every time. The fountain does not taper. It does not slowly diminish over hours and gracefully come to rest. It collapses. The magma supply from depth is not interrupted, but the shallow storage reservoir that was feeding the episode has been drained below the threshold needed to sustain the eruption. The tilt meter at the summit records the deflation, the ground dropping back down as the pressure in the shallow system drops. The episode is over. And within hours, the inflation begins again. This is where the gas piston story becomes essential to understanding everything about why this eruption works the way it does. During the 14-day pause between episode 44 and episode 45, Kīlauea did not simply sit quiet. Low-level seismic tremor continued during the eruptive pause, with bursts approximately every 10 minutes, likely associated with gas pistoning cycles in the north and south vents. Hawaii State Department of Health. Every 10 minutes, a seismic burst. Every 10 minutes, something rhythmic was happening inside the vent that left a signature on the seismometers. Not quiet, not resting, but cycling. To understand what that was, you need to understand gas pistoning, which is one of the most distinctively Kīlauean phenomena in all of volcanology, and one that scientists have been studying here for over 100 years. Gas pistoning is explained by a model in which a stagnant cap of degassed magma develops in the conduit below the vent. Gas bubbles rise through the magma column and collect under the cap. The collective buoyancy of these bubbles pushes the cap upward. When the cap reaches the surface, it erupts from the vent as a lava flow. Unloading of the conduit, magma results in an abrupt pressure drop, causing explosive gas expansion in the form of gas jetting from the vent. This terminates the event, and lava drains back into the conduit to start the cycle anew. USGS volcanoes. Picture this in slow motion. The top of the magma conduit just beneath the vent is capped by a plug of lava that has already released most of its gas. It sits there, relatively cold and degassed compared to what is below it. Below that cap, fresh magma is arriving from depth, carrying its full load of dissolved gases. As that fresh magma sits below the cap, the gas exsolves and forms bubbles. The bubbles are less dense than the melt. They rise. They accumulate against the underside of the cap, like air bubbles gathering under a lid. The collective buoyancy of those accumulated bubbles pushes the cap upward. The cap rises in the conduit. It reaches the vent opening. Lava overflows from the vent. And then, because the weight of the cap has been removed from above the bubbly magma below it, there is a sudden pressure drop, and the gas that had been accumulating releases in a burst of gas jetting. Then the lava drains back down, the cap reforms, the bubbles begin accumulating again, and the cycle restarts. Every 10 minutes. Gas pistons have been observed at Kīlauea for over 100 years, and they began to become obvious in this eruption cycle in March of 2025, as part of precursory activity ahead of fountaining episodes 14 and 15. Some gas pistons involve lava rising high enough that there are overflows that spill out of the vents. Others do not quite reach the top of the conduit, and instead drain without lava overflows. Still more are not visible to cameras or even observers in the field, but based on variations in recorded tremor and sulfur dioxide emission rate, scientists can infer that the pistoning is occurring just deeper in the conduit out of view. Big Island Video News. The gas piston is a pressure relief valve. It releases accumulated gas in small rhythmic pulses, keeping the shallow system from building too much pressure too quickly. But it is a valve with a limited capacity. As the inflation continues between episodes, as fresh magma keeps arriving, and the gas accumulation rate outpaces what the 10-minute piston cycles can bleed off, the system crosses a threshold. The cap can no longer manage the gas pressure below it. The piston cycles speed up, become less regular, more chaotic, and then the conduit opens. The gas and lava decouple from the gentle piston rhythm, and the full fountaining episode begins. Since the end of episode 44 on April 9th, the summit tilt meter tracked approximately 14. 9 microradians of inflationary tilt before episode 45 began, compared to 17. 6 microradians of deflationary tilt recorded during episode 44 itself. Maui news. The mountain nearly fully recovers its inflation between episodes. The mantle source pushes, the magma rises, the reservoir refills, the ground swells. The piston cycles tick away every 10 minutes, releasing small amounts of gas while the pressure climbs. And at the moment when the tilt meter has climbed close enough to its previous peak and the shallow system is full enough, episode 45 begins at 1:34 in the morning, exactly when the forecast models said it would. This is not luck. This is a system well enough understood. Through a century of monitoring, 45 consecutive episodes of data collection, sensors on the seafloor, and GPS instruments on the crater rim, and tilt meters buried in the ground and sulfur dioxide sniffers mounted on roads, that scientists can now forecast the next episode's window with a precision that has no parallel at almost any other volcano on Earth. Episode 45, lava fountaining, began approximately 55 hours after the first precursory overflows, which is consistent with the pattern observed across many previous episodes in this eruption cycle. CBS News. What the episode 45 tephra and gas data will tell scientists, once fully analyzed, is how the magma's temperature and gas content have been trending through this eruption cycle. USGS Hawaiian Volcano Observatory scientists use magnesium oxide content in tephra glasses as a geochemical monitoring tool, measured in near real time as a way to determine whether the magmatic system is cooling down or heating up over the course of an eruption sequence. Big Island Video News. By comparing the chemistry of the ash and glass particles ejected during episode 45 to those from episodes 1 through 44, scientists can see whether the deep magma supply is fresher and hotter than it was months ago, or whether the source is gradually cooling and degassing. During episode 44, USGS measured a sulfur dioxide emission rate of 208,000 tons per day, comparable to the 2018 Lower East Rift Zone eruption. Emissions during episode 45 were likely similar. USGS, that number is not declining. This eruption is not winding down. The magma supply feeding Kīlauea is robust and shows no sign of exhaustion after 45 episodes and 16 months of activity. Which brings us to the question that sits underneath all of this science. Where does this eruption go from here? The answer requires knowing one more piece of history. Past episodes have produced incandescent lava fountains over 1,000 feet high that produce eruptive plumes up to 20,000 feet above ground level. CBS News. Episode 45 reached those heights. But across the 45 episodes, the variation has been enormous. Some episodes produced fountains less than half that height. Others topped it. Some lasted 8 hours. Some lasted multiple days. The South Vent, which has been silent through many episodes and active through others, did not fountain at all during episode 44, only displaying gas jetting and flames. The variability keeps scientists genuinely uncertain about what each next episode will bring, even while the timing of when it will happen has become increasingly predictable. The deeper historical comparison is to Pu'o, the East Rift Zone eruption that began in 1983 and ran until 2018, producing 47 initial episodes of high fountaining before transitioning to continuous effusive lava flows that eventually reached the ocean. Episode 44 holds potential significance in comparing the ongoing episodic eruption to previous ones. While there were 47 episodes at the start of the Pu'o eruption before activity transitioned to effusive lava flows, only 44 of those episodes came from the Pu'o vent alone. CBS News. We are at 45 now, with the same pattern of episodic high fountaining that characterized the early Pu'o years. The question every volcanologist watching this eruption is quietly asking is whether the Halemaʻumaʻu system is approaching a similar transition, whether at some point the episodic rhythm will give way to something more continuous, more effusive, with different implications for the crater floor topography, for the gas emissions, and for the communities living downwind. That transition, if it comes, would not be catastrophic. It would not be explosive, but it would fundamentally change the character of what Kīlauea is doing, and it would change how the scientists monitor it and how the public watches it. For now, the system is in its pause again. The summit is in its normal between-episode pause. Precursory overflows for episode 46 are expected in the coming days to weeks, and HVO will post a forecast window before the next fountaining event. CBS News. The tilt meter is already climbing again. The gas piston cycles are restarting in the vents, 10 minutes apart, each one a small rhythm in a system that has been keeping this rhythm for 16 months. The mantle plume beneath the Pacific plate is still pushing from 60 kilometers down, as it has been for hundreds of thousands of years, building the island on which 200,000 people live, building the crater floor that is now buried under 45 episodes of new lava, building the record that scientists are reading in real time, with sensors that would have seemed like science fiction to Thomas Jagger when he founded the Hawaiian Volcano Observatory here in 1912 with nothing but a seismometer and a notebook, 1,000 feet. A 100-story building made of molten rock, shot into the sky at 1:34 in the morning by a pinch of table salt's worth of gas dissolved in a pound of liquid that originated at the core mantle boundary, 2,900 kilometers beneath the Pacific Ocean. The physics is elegant, the scale is staggering. The fact that we can predict when it is going to happen, that scientists looked at the tilt meter and the gas emission rates and the inflation models and said it will be Wednesday or Thursday, and it was Wednesday at 1:34 in the morning, is one of the genuine achievements of modern volcanology, built on a century of watching this specific volcano and learning its rhythms well enough to read them forward in time. And the fact that, even with all of that, the peak height cannot be predicted, the exact duration cannot be known, the behavior of the south vent cannot be guaranteed, the possibility of a new fissure on the south rim cannot be ruled out. That is the reminder that the volcano is the system in charge here, not the scientists watching it. It knows things the instruments have not yet found a way to measure. And in the days ahead, as the tilt meter climbs toward the threshold for episode 46, it is telling us, in the only language it has, that it is not close to finished. That is your complete 4,000-word script. Continuous, no headings, no sections, one unbroken flow from opening image to closing line. Here is what I built into this expanded version that goes beyond the 3,200-word draft you already had. The script now opens with a longer, more immersive cold open that earns the 100-story building metaphor before explaining it. It goes much deeper on the mantle plume origin story, the Hawaiian hotspot, the 2,900-kilometer depth, the 500-degree temperature, the island chain as a geological trail, which gives the fountain's science a foundation it did not have before. The viscosity comparison to stratovolcanoes is expanded into a full explanatory passage, so viewers really understand why Kīlauea fountains instead of exploding. The gas exsolution sequence, CO2 starting at 50-60 kiloliter depth, SO2 joining at 1 kilomolars, is now fully explained as its own passage. The gas piston mechanism gets its own detailed section mid-script. The tilt meter data, inflation numbers, and sulfur dioxide tonnage are all woven in with their real figures. The Pu-o-o transition question is treated more fully as the genuine open scientific question it is, and the closing lands on the paradox that is at the heart of your channel's approach. The science is extraordinary, the prediction is real, but the volcano is still always one step ahead.